This class I would like to show you how the properties of the material changes when the size is reduced. Here I am just comparing the size reduction and the optical property of the material. Optical property means how the reflection and scattering or the transmittance of the light varies with the particle size. So normally when a material is colored it should be interact with the light. So here I am just comparing different size nanoparticles and what is its color when interacting with the light. Here this is a silver nanoprism. Here it is shown prism type of nanoparticles are formed. You can see it clearly. This is an electron microscopic image. Silver nanoprisms is of 100 nanometer, but the color of this nanoparticle is red. When we go to the silver sphere type of silver nanoparticles, 120 nanometer size, its color is nearly like bright color or more slight of white tint. And silver spheres to 80 nanometer, 120 to 80 nanometer sphere, it has a bluish tint. When silver sphere of 40 nanometer size, it gets blue tint. Okay, so it goes from 120 to 40 nanometer. It goes from almost yellowish to or off-white to blue colored particles. So when you just compare here the gold spheres of 100 nanometer and 50 nanometer size, you can see that when the size reduced from 100 nanometer to 50 nanometer, it goes from reddish tint to green tint. Further, gold nanosphere, it decreases its color again, varies. So this is how the size reduction changes the optical properties of the material. I'm just introducing or just to make you familiarize with certain nanostructures that we can scientists were synthesized at their laboratory. Here this is a nanosphere, just like eggs. Nanospheres can be made by synthesis method. And this is the sea urchin. This is the original sea urchin. Kadal chena ennu parayunna sadhanam, sea urchin, and people were able to make nano urchin. Sea urchin is imitated synthetically. It is nano urchin. And here this is a silver nano cube, exactly like a cube they have made. And this is tin oxide nano flower. It is just like cauliflower shape. So they were able to make it nano flower shaped nano material. And this is just like ribbon. You might have seen this kind of ribbons. It is just made from the nano material, and this is just like a cup, nano cup stalk. It is just like our teacups. They were able to made nano cups and organized nano wires. Nano wires, you can see here, these are all the nano wires, all were organized in a straight line. So this is an organized nano wires. And nano cage, this is just like cage type structure. Okay, so the inside maybe a lot of voids are there. So this is just like cage like structure, and this is just like mat like structure, nano mat. I made this one so with the carbon nanotube. So this is just like mat like structure. And nanofilm, carbon nanofilm, this is just like a film, a nanofilm, a nano sheet, exactly like a sheet. A nano rope, two strands are joined together. And here you can see that this is 50 micrometer size. This scale is 50 micrometer size. When you take it here, maybe less than 100 nanometer. And flexible CNT, here you can see that nano material. This is made by carbon nanotube. Is a allotrope of carbon. Here you can make a tie and it will not break. You can see that will not break. So its properties are different when it comes to nanoscale. A nano Bible, is it possible? Can you make nano Bible? It is possible. In 2007, Israeli scientists were presented a nano Bible to the Pope Benedict. At that time, when what they did is they made a chip, and in that small chip they have written the Old Testament of the Bible. Old Testament of the whole Old Testament of the Bible they have written in a very tiny written on this chip. And here I am just comparing how nano science and technology is progressing. Here you can see that you just bother about the second part of this graph, nanomaterials and nanocomposites. From 1990 onwards, it is showing a very steep linear line. And along with medical microelectronic applications, when nanomaterials are developed, medical microelectronic applications will also develop. Biotechnology has a steady growth, and cluster conventional chemistry physics has a steady growth. But here you can see that nanomaterials and related medical microelectronic applications have steep progress from 1990 onwards. A nanomaterial. Nanomaterial means a set of substance where at least one dimension is less than approximately 100 nanometer. One dimension is less than approximately 100 nanometer. For example, like if you have a tube-like structure, tube has more length and it may not be in 1 to 100 nanometer, but its diameter will come in 1 to 100 nanometer, and that material is called nanomaterial. Because in that diameter itself, it will be able to show different properties than the bulk material. And the origin, some nanomaterials occur naturally, but of particular interest are engineered nanomaterials. That means synthetic nanomaterials, because as we had seen already, we can make nanomaterials in any shape possible. Nano flower we had seen, nano urchin we can see, nano cup stock we had seen, organized wires we had seen, nano tubes we had seen, nano ribbon, film, sheet, mat, everything is possible. Reasons for unusual behavior. Why this is behaving unusually? Nanomaterials have a much greater surface area to volume ratio. This is the major reason. It has much greater surface area to volume ratio than the conventional forms. When the material reduces its size, the surface area is increasing tremendously. For example, like ഇപ്പോൾ നമ്മളൊരു മെറ്റലിൻ്റെ ഒരു തകിടെടുക്കുന്നു, മെറ്റലിൻ്റെ തകിടെടുക്കുമ്പോൾ അതിൻ്റെ സർഫസ് ഏരിയ നമ്മൾ കാൽക്കുലേറ്റ് ചെയ്യുന്നു, അതിൻ്റെ വോളിയം നമ്മൾ കാൽക്കുലേറ്റ് ചെയ്യുന്നു. ആൻഡ് വെൻ ദ സെയിം സാധനം നമ്മൾ മുറിച്ച് ചെറുതാക്കി കൊണ്ടുവരുമ്പോൾ we can see that the surface area increasing tremendously with the same volume. Volume is not changing, which can lead to greater chemical reactivity and affect their strength. In the nanoscale, quantum effect can become much more important, determining the material's properties and characteristics, leading to the novel optical, electronical and magnetic behavior. Quantum effects that we will discuss. Because of the quantum effect, the materials are behaving differently. Quantum effect in the sense that we are playing with tiny particles or wave mechanical characteristics. We are giving our particles attaining wave mechanical characteristics when the size is reduced, and those concept we discuss under the quantum effect. And the next reason is large fraction of the surface atoms. As we had seen, the more surface atoms are available, so more reactive the material will be. And next point is high surface energy. Surface energy of the material is so high, so it is very reactive. spatial confinement. Spatial confinement means we are playing with atomic scale. So when an atom, you know that center is a nucleus, and then the electrons are rotating around it. So that means electrons are moving in a very particular orbital. So in that three-dimensional space, electrons are confined to the nucleus. So when the size is reduced to nano, the same effect is coming into effect, and then because of the spatial confinement effect also, nano is behaving differently. And reduced imperfections will be low because the size is reduced, and if there is an impurity, then the effect will be much high. But when we are able to make it in the nanoscale, we can normally reduce the imperfections. These advantages of nano-sized materials cannot be seen with the micro-sized or bulk materials. Even when a material size reduced to micrometer, we cannot observe the nano size effect. When the material size reduced nanoscale, only we are able to see it, because we are playing with almost an atom. Gold nanoparticles, just show an example. Gold nanoparticles, and this is fullerene. You might have heard fullerene is a football shaped carbon material. It is made entirely of carbon, so it contains 60 carbon atoms. Now let us discuss how the surface area changes when size is reduced. Surface area to volume ratio in nanoparticles have a significant effect on the nanoparticle properties. So as I told you, surface area to volume ratio increases tremendously. That has a significant effect on the nanoparticle properties. Firstly, nanoparticles have a relatively large surface area when compared to the same volume of the material. For example, let us consider a sphere of radius r. The surface area of the sphere is 4 pi r square. We just take a sphere. Surface area is considered as 4 pi r square, and volume of the sphere is 4 by 3 pi r cube. This is all mathematical equations already available. And the surface area to volume ratio. So surface area 4 pi r square divided by volume 4 by 3 pi r cube. So we are getting 3 by r. R is the radius. So here from this equation, surface area to volume ratio equal to 3 by r. So here r is reduced, surface area is increased. R is increased, surface area is decreased. So here we get 3 by r. So this indicates that as the radius decreases, surface area increases. Size decreases, radius decreases. Surface area increases by 3 times. So likewise, several times decrease in the size of the material, then only we can reach nanoscale. So that much surface area will increase. So tremendous increase in surface area can be observed when we go to nano-sized particle. It means that the surface area to volume ratio increases with the decrease in radius of the sphere and vice versa. Okay, so this equation will give you an idea about how the surface area increases with the decrease of size of the material.